Okay, welcome to Unit 5A, Exponential Functions. Day 1, we're going to look at what exponential functions are. You have looked at these before in Algebra 1 and even more in Algebra 2, so this should not be new. So in biology class, we're looking at bacteria cells under a microscope. At the beginning of class, you see 2. And you notice that every minute, they double in number. Let's complete this table. So at the beginning, at t equals 0, we have 2. A minute later, we have 4, 8, 16, 32, 64, and then we have 128 bacteria cells after 6 minutes. And now we can plot these points on the graph where the t-axis is the horizontal axis and the number of cells n-axis is the vertical axis. So I plotted as many dots as I could on this grid. And you can see that this graph was going to go something like this. And that is an exponential graph. So what can we do to model this equation? Well, I'm going to use n as the number of cells. And it's going to be an equation like this, where this number up front is the initial value. So the 2 up front is the initial value. That's what I had when t is equal to 0. This 2 here is because they're doubling. Every minute. And you can see that this is an exponential growth. The graph where the number of cells is growing over time. So exponential functions are multiplicative. In other words, it's continuous multiplication. You have an initial value that you begin with, and then you keep on multiplying over and over and over again. This is the form for it. Sometimes they use a t instead of an x. Where this b is the change factor. It's the constant multiplier. It's the same multiplier over and over and over again. It must be positive and cannot equal 1 because multiplying by 1 does not change anything. This function is changing over time, over and over and over again. Well, let's look at a problem where we have a population of a small town modeled by this equation that's growing at 2.4% per year. So what does p of 0 mean? P of 0, well, if I plug 0 in here, which I don't really have to because you should know what p of 0 means, this becomes 1, so p of 0 is equal to that number up front, the 5280. And this is the initial population of this town. If you notice, it's right here on the graph, right on the y-axis. So how can you tell that this is increasing? Just by looking at the equation. If you look at this equation, this number right here is the b value, and b is greater than 1, and that means it's multiplier. So another name for that b value is the multiplier. The multiplier is greater than 1. That means it's growing. If you multiply by something bigger than 1, you're going to grow, grow, grow. Then it says use the graph to estimate when this population is equal to 10,560. Well, this is 10,000. 10,560 is probably right around here. That's a horizontal. I'm going to come vertically down the best I can. And if this is 10, this is 20, this is 30. I'm going to say close to 30 years. I don't know. Maybe something like 29. It's hard to tell exactly what it is. So using my equation I circled in red, what's the population of 10 years? Well, I'm just going to plug 10 in here. 5280, 1.024 raised to the 10. And I'm going to go to my calculator to do that calculation. I go to my calculator, I put it in, I hit enter, and I get 6693.195, but this is a population equation. We cannot have decimal amount of people for population. We can have decimal amount of millions of people, but this is not in millions, it's just regular population. I cannot have decimal amount of people, so my result is 6693. So you see I put down my result of 6693, and population cannot have decimals. So what does this mean? So I'm going to put this in my calculator, or I'm going to write it out first. And I went to my calculator, and my calculator told me this. No decimals again. And what does this really mean? This is the population from 30 years ago. So whatever year it is now, that was the population 30 years ago. And then finally, the last part, we're going to use our graphing calculator. You have to have a calculator for this part. So what we're going to do, we're going to go on our calculator. We're going to make y1 is equal to the equation 5280 1.024 to the x. Y2 is going to be the population we want, 10,560. So we're going to go to the calculator to see what happens. So I put these two equations into the calculator. I use my y equals on the top left here. I put in 5280 parentheses 1.024 raised to the x. The x key is this key right here that says xt theta n. And then my second equation is 10,560. And I don't hit graph. I'm going to hit the set the window. So what I need to do is pick a good window. So for me, a good window would be, well, x stands for number of years, and y stands for the population. So you have to know what x and y stands for. X is always going to stand for time in exponential. In this case, years. It could be days, hours, minutes, whatever it is. The first example we had on the front page, it was minutes. So I'm going to go from 0 to, well, I said it was about 30. I'm going to go over 30. I'm going to go to 40 years. My minimum population is 0. I want to get to at least 10,560, so I'm going to go to 15,000 as my population. And now when I hit graph, it's going to graph it on this window. There's the exponential, and there is a horizontal line, and I got to see where they intersect. So hopefully you remember where they intersect, and I'll write it on the notes. I'm going to hit the blue second. I'm going to hit the trace key. And I have options that I could figure out, calculate things on graphs, and one of the things I could calculate is number 5. Intersect, and it's going to ask you for the two curves. You don't have to do much. Enter, enter. If they intersect more than once, you got to put it to the closer intersection that you want. Well, this one only intersects once here, so there it is. And right here at the bottom, it gives me my x value of the intersection. And obviously the y is going to be 10,560 because that's what I wanted. The x value of the intersection is this number here that I'm circling. So I put here the window that I use, x min and x max, y min and y max. I kind of sketched what the graphs look like. I did the second trace, number 5 intersection. I found that the intersection was at 29.226 years. That's how long it takes for this population to double from 5280 to 10,560. Next page, a very similar problem, except that we have v of t equals 8,000 times 0.95 raised to the t. It's a volume of a balloon deflating 5% per each day. So my time in this case for t is days. The other one was years. So v is 0. Again, it's really unnecessary because I think it is quite obvious when you plug in 0 for the exponents. I get v of 0. Is it 8,000, and it's, I'll pick, I didn't really give it units, I'm just going to call it milliliters. Okay, so this is the initial volume. Let's see, on day 0. So again, how can we tell that this balloon is deflating? Well, off my equation here, this b value is less than 1. That means my multiplier is less than 1. If you keep on multiplying by something smaller than 1, you are going to be deflating or decreasing or whatever you want to call it. So right here is about 8,000. Then it says estimate when it is equal to 4,000. So I don't know, maybe 4,000 is right around here. Go across this way, come down. Well, if this is 5, this is 10, this is 15. I'm going to say close to 15 days. I could tell it's less than 15 days, so maybe it's 14 days, something like that. Who knows? We'll have to see what's going on here. And then I'm going to use my equation that I circled in pink, and I'm going to figure it out for 3 days, 4.5 days, and even 20 days later. I'm going to put this in my calculator to do all that. So I did all my calculations, and I notice I have decimals here because this is volume. Volume can have decimals. Populations of people cannot, but volumes definitely can have decimals. So now I'm going to do the one where it says v of -3. V of -3 is going to be the 8,000 times 0.95 raised to -3. I get 9330.81 milliliters on my, put them in my calculator. And this is the volume 3 days before what I consider day 0. I'm going to do the graphing calculator again, except this time I'm going to make my y1 equal to the 8,000.95 raised to the x. Y2 is half this volume, which is 4,000. And I have to set a good window, and then I have to see where they intersect. So I'm going to go to my calculator to do all that. So there are my two things I want, the original equation for the exponential, and then the volume equal to 4,000. And if I hit the word graph right now, it will use that last window that I had, which is not a good window for this problem. So I'm going to change this window. I think we said about 15 days, so I'm going to change my x max to 20 days. This might have been okay, but I think I only need up to 8,000. That'll show the whole exponential. And now when I air graph, I'm going to see the exponential in blue and then the horizontal line in red. And I see where they intersect. So again, I'm going to do my second trace, number 5. I don't have to do anything special than hit enter a few times. And you can see right here, I'm seeing they intersect right at 13.513 days, and I'm going to go put all this information on my notes. So here's all the information that I did on my calculator. The two graphs I sketched out, I saw where they intersect about 13.513 days. Part G asks, what does the right side of the graph do? You can look here at Y1, or let's go back to the original graph at the top. I'm not seeing the whole right side, but I think what we're seeing is that the graph is not really going up or down forever. It's kind of really just getting flatter and flatter. Or what we know to say is that the graph levels off to approach the x-axis, or the volume is equal to 0. And we know what this is called. We've done this before. When things level off, it is a horizontal asymptote. These type of graphs are always going to have a horizontal asymptote, but just on one end only. So we're going to look at two type of graphs, the exponential growth and the decay equations. Something is growth when that b value, that something inside of parentheses, is going to be bigger than 1. The a is the initial value. This r value is some percent that will be given to you in a problem. You cannot use a percent. You must change the percent to a decimal, so the r value is equal to the percent divided by 100. And then the 1 plus the r is the b value that goes inside the parentheses, and I use the variable x or t in my equation. So for an example, if I have initial equals 100, and it grows by 8.2%, my equation would be 100, 1.082 raised to the x, because 8.2% is the number 0.082. I had to add it to 1. I say initially I have 3.2, and it grows by 150%. Well, then I would have y equals 3.2 times 2.5 raised to the x. And the reason that works is because 150% would be 150 over 100, which is the number 1.5. I have to add 1 to it, so I get a 2.5. Something could grow by more than 100%. Conversely, when we have things that are decaying, we have a change factor or b-value that's between 0 and 1. It can't be negative, can't be 0, can't be 1. Some decimal between 0 and 1. A is still the initial. I still have this r percent, except now I'm going to do 1 minus r as a number inside of parentheses. So let's say initial equals 100, and it decays by 8.2%. Well, I still have the same decimals before, except now I'm going to do 1 minus. So y equals 100.918 to the x. And let's say I have initial equals 3.2. It decays by 150%. And you say that's impossible. You cannot lose more than 100% of something. Okay? So the way I look at these numbers inside the parentheses, these numbers tell me how far away from one I am. So this is 8.2% away from 1. This is 1.5 or 150% away from 1. 8.2% away from 1. 1.5 or 150% away from 1. And this is below 1, but it is 8.2% below 1. It's only below 1 because it's decaying. So let's look at some examples here. I want to know if it's growth or decay, the decay factor, and the decay rate. They're not the same thing. The factor is the number inside of parentheses. The rate is the percent growth or decay. So this one, this b is bigger than 1, is definitely growth. The decay factor is a number inside the parentheses, which is 1.2. And I ask myself, how far away is that from 1, which is 0.2, which is 20%. If you know how to change a decimal to a percent, you just take the decimal and you multiply it by 100. And it gives you your 20%. The next one over here, well, let's see. This number is below 1, so it's definitely decay. This b value is 0.75. How far away is that number from 1? I get a decimal 0.25, which is 25%. It's decaying by 25%, not 75%, 25%. Next one, here's my b value. It's below 1, it's definitely decay. The number here is 0.912. If I do that away from 1, to me I get 0.088, which is 8.8%. And this last one is my b value. It's definitely bigger than 1. It's growing. The b value is equal to 2.5. How much bigger than 1 is it? It's 1.5, and 1.5 times 100 is 150%. It is growing by 150%. Okay, for this example, you signed a 30-day contract. Offer 1 is you paid you $100 on the first day, $200 on the second day, $300 on the third day, and so on and so forth, so on. What type of function is this? This is a linear function because you're increasing by the same amount each day. Day 1, 100. Day 2, 200. And so on and so forth. Okay? It grows by $100 each day. So what's the model for this? Well, P is my pay. I would say 100N, where N is the number of day. That's the model. Or offer 2, he's going to pay you a penny in the first day, 2 pennies in the next day, 4 in the next, and he's going to double. What type of function is this? This is exponential because of this doubling idea. Doubling is a multiplier. First one is adding 100 each day, which is linear, and this one is doubling. So day 1, you get a penny. Day 2, you get 2 cents. Day 3, you get 4 cents, and so on and so forth. This is your model for this one. 0.01 is your initial amount. Doubling is the number 2. And we have to do n minus 1 because we want to plug in day 1. And we'd have to do 1 minus 1 to get something raised to the 0. So these are our 2 options that we have to get paid. Which option do you prefer? I'm going to be honest. The second option, it's not even close. Okay. You don't think it's going to add up? It adds up incredibly. So if I do this exponential in my calculator, I do P after 30 days, 0.01 to the 29th power. So you see I went ahead and I put in 30 days for the exponential and 30 days for the linear. Well, the linear is going to be easy. 100 times 30 is $3,000. The exponential, even though it starts at a penny, it grows and grows and grows. And by the end of the 3rd week, you see that it is incredibly growing. So after 30 days, which means I have to raise it to the 29th power, you have over $5 million to get paid on that 30th day. It's not even close. So comparing the two on one graph, I just did this by hand. I didn't put it in the calculator. I see that the exponential goes very slow to begin with, and the linear is just, a diagonal line. And on about day 19, the exponential catches the linear function, and basically it turns out to be this. Once an exponential overtakes the linear function, it is game over. Exponential dominates the linear function. The linear function might be ahead for a little bit, but once the exponential catches up to it, it's done, it's over. Okay, let's do some examples. If I just give you any 2 points, it could be a linear function or it could be an exponential function, as you see on the right here. So we have to be specifically what we want to do. I would have to give you more information. So let's talk about what we want. I'm going to write an exponential function. Y equals a times b to the x. And how lucky do I have? I have the initial amount right here. So a equals 2. So right now I have y equals 2 times b to the x. And then I can use this other order pair, put it in for the x and the y. I get divide by 2. I get 81 is equal to b to the 4th. And then I'm going to take the 4th root. I get b equals 3. And an equation for this function is going to be 2 parentheses 3 to the x. Well, a linear function, one way to write a linear function is y equals mx plus b. And again, I have the initial amount, or the b value, is equal to 2. Now I want to figure out the slope. Pretty much slope is change in y over change in x, which is in this case is 160 over 4, so I have a slope of 40. So I could say this function equals 40x plus 2, and both these equations go through both those points. Now for this next example, I don't have the initial point, so I don't know the a value for the exponential or the y-intercept b value for the linear one. I'm going to do the linear one first anyways because we've done enough lines. I still have to figure out my slope here. So change in y over change in x is going to be 6 minus 24 over 3 minus 2, negative 18 over 1, or negative 18. So I get y equals negative 18 parentheses x. I'll just do the 224 as my point. That's one way to write it. If you wanted to expand it out even more, you could do negative 18x plus 36 plus 24 and get g of x is equal to negative 18x plus 60 if you wanted to. The hard part here is going to be doing the exponential. It's still going to be y equals a times b to the x, but I don't know a, I don't know b, so I have to do a system. I have to do one equation over the other. Okay, I'm going to use this one. Let me grab pink. I'm always going to grab this one first because I have to use the higher x first. So 6 is equal to a times b to the third. Always put the higher x on top. Underneath it, I'm going to use the other point. 24 equals a times b squared. And what I'm going to do, I'm going to divide them out. One, because the a's cancel, and then I could just subtract my exponents. So 6 over 24 is 1/4, and b 3 over b2 is just b to the first. I have my b value. So right now I could plug in, I have y equals a times 1/4 to the x. I can choose any order pair I want. I'm going to use the 224. 24 equals a times 1/4 squared, which is a times 1 over 16. I get 1 over 16, I'm going to multiply by 16 on both sides. I get a equals 384. Or my function is going to be 384 1/4 to the x. Negative slope, because it was decreasing linearly, or 1/4 smaller than 1, it is an exponential decay. So when I look at information, how can I tell if something is an exponential or linear function? Well, exponential function is because I have a constant percent or multiplier. That's what I'm looking for. I have repeated multiplication, which is a percent or a ratio. And a linear function has a constant rate or constant adding amount or subtracting amount. So when I look at these two tables, the first table I see that between here and between here and between here, it's always adding 15, adding 15, adding 15. So I know it's linear. I'm adding the same amount every single time. So again, if it's linear, I have a slope. My slope is change in y over change in x, and I can see my change in y is 15. My change in x is 5. So my slope is equal to 3. I can just do y equals 3 parentheses x minus 30 plus 30 by using that first point. And if I expand it out, I get 3x minus 90 plus 30. Y equals 3x minus 60 is the equation. Oh, not y. Let me call it the right thing. F of x. Because I said f of x. For this next example, I see, oh, it's multiplying by 1.2, multiplying by 1.2, multiplying by 1.2. So that means it's exponential because it has a constant multiplier. I don't have the initial amount. We need x equals 0 to have the initial amount. And 1.2 might be it, but my x's is 5. So I'm going to set up a system. I'm going to do, let me pick a different color. 1200 equals a times b to the 10th over 1000 equals a times b to the 5th. The a's cancel out. I get 1.2. That number again is equal to b to the 5th. I take the 5th root. I get b is about 1.037. So I'm going to use this as my x and my y. So I have 1000 equals a times 1.037 to the 5th. And to figure out my a value, I'm just going to divide by 1.037 to the 5th. I don't even care what 1.037 to the 5th is. If I do all that, I get an a value is equal to 833.333. And when I'm done, I have g of x is equal to 833.333 1.037 raised to the x is the equation for that exponential in this table. Bigger than 1, growing, increasing values, positive slope.